Welcome to Chapter 18. If you watched Chapter 17 first, you know that that was all about what is a multiple regression model. Chapter 18 is, well, how do I build a good one? So if you haven't viewed 17, please do so before viewing 18. Okay, so the first thing we're going to talk about is what's called an indicator or dummy variable. So I want you to think about riding a roller coaster because that's the data we're going to be dealing with. The first thing we want to look at when it comes to riding a roller coaster is we want to ask, hey, what makes a good one? Is it speed, height, duration, so length of time of the ride, inversions, or something else? So some of the things you look at with these variables you would expect to be very correlated with each other, like, speed and duration, or maybe length of the ride and duration. So we'd expect these to be related. Let's investigate that relationship and see what we can predict. So this is a scatter plot of a sample of worldwide roller coasters that we're going to be dealing with in our mini-tab examples this week as well. And if you look at it, this is a pretty good linear relationship. It appears that duration and length are related. It isn't a perfect relationship, but it's pretty strong. There's some scatter present. There's a couple values that are a little questionable, like the coaster we see down here. That guy's a little bit questionable. He might be an outlier. But as we'll see, we'll have better ways of figuring out whether or not things are outliers or otherwise in this chapter. So if you do a residual plot for just those two, so you did the linear regression, you come up with the residual, the conditions seem to be met. This looks pretty equally spread. Nothing questionable there. It looks like we're ready to rock and roll with some linear regression action. Okay, so here is the linear regression output for doing length versus duration for these data. I want you to pay particular attention to the coefficient for length. That's your slope, this guy right here. If you're looking at this value and thinking, ooh, well, that's kind of small, but remember, this is telling you like length of the roller coaster, time you spend on it in seconds. So we multiply this by 1,000. That tells us that for every 1,000 feet of track, we get about a 23-second longer ride. All right. So one of the big factors when it comes to predicting length of the ride or how long it's going to take to or duration, sorry, I was going to say how long it's going to take to ride the ride, which is duration, is whether or not the roller coaster has inversions. In case you didn't know, an inversion is like a corkscrew where the individual riders end up upside down at some point. The big thing that's difficult about these is if you're going too fast, you'll fly off the inversion. If you're going too slow, you won't make it through the loop. So there's some certain limitations on speed and length that are required in order for you to have an inversion. So we got to be careful with what inversions actually do to our records for our coasters. So if you separate the data into those who have inversions, that's in red over here, and those without inversions, that's in blue, we notice a distinct difference between these two. When you compare these two lines, I'm hoping you notice that there are a couple things that are different about these. In particular, well, when you think about lines, they have two characteristics, slope and intercept. If you look at the intercepts, they look different. The red line is slightly above the blue line. If you look at slope, well, those look about the same. So what I want to do is I want to create some way to change the intercept based on whether or not I have inversions. Okay, so in how we do this is we create what's called a dummy variable. If you've never heard the word dummy variable before, it's not because it's dumb, it's because it just holds a place and does one thing. This is also called an indicator. I like indicator better simply because it sounds more like what it actually does. It's like your indicator light on your car, which, by the way, that's your turn signal. When you click it, it flashes on and off, and when you don't click it, it's completely off. So that's exactly how this behaves. If the inversion is equal to a 1, it's on, it's a yes, and it's equal to a 0 if there is no inversion, and then it's a no. So basically, it looks at all the coasters and it says, oh, if it has inversions, dude, we turn this on. Dude, that was supposed to be like lights turning on, I'm sorry. And if we don't have an inversion, we have the indicator going off, and it's representing a no. Okay. Cool. So here's how this works. We have this indicator. Remember, the indicator inversions is only a 0 or a 1. That's it. It can only be a 0 or a 1. And as you look at this, we reanalyze our linear regression with this indicator present, and hey, it looks significant. That's a very small p-value. Additionally, if you look at this, the r squared is much larger. But remember, r squared is sensitive to the presence of a new variable, so it inflates a little bit quicker. But even the r squared adjusted, the one you should be paying attention to, here, let me highlight that. That one is larger for this model as well. So it appears that adding inversions did improve our model quite significantly. And it's significant because when we look at the p-value and the t-ratio, they are both significant, and therefore this is going to be something we want to include in our model. So what does inversions actually do? Well, when you have an inversion, inversion's a 1. And so this value right here for inversions will be a 1. So I just got a 1 times this number, so that'll give it itself. Oh, and then since this doesn't have a variable on it, I can combine it with the intercept, since they are like. So it basically just shifts the intercept up about 30 seconds, or makes each ride longer by about 30 seconds. And it's about 30 because that's the coefficient on inversions. Alrighty. So what do you do if you want to have more than one indicator? As in, what if I want to take on more values other than just 0 and 1? So if you want to do something like, say, include birth dates or something crazy, or birth month, where there's 12 different options that you want to include, and they're categorical. So how do I deal with 3 or more categorical variables? Well, I introduce k different indicators. Okay, so if I have k levels to my categories, then I want just slightly one less indicator than what we have present. Let me show you how this looks with an example. So for instance, if you wanted to have birthdays, you would make 1 January, 2 February, so on and so forth. 12 December? No, that is horrible. And it's going to inflate everything by the number that you have that you're using for each month. That's the worst way for you to do this. We want 1 and 0 because that either turns on or turns off. And it doesn't create a factor where it multiplies everything and makes it difficult to interpret that value, the coefficient. What we instead do is we would introduce 11 indicator variables that either turn on or off based on that month being present, and then we have some baseline default month, in this case it would probably be January, that is the one that's on if all the rest of them are off. That's all it does. Okay, so here's an example for you involving the Texas Traffic Institute. We've looked at this data once before, but it's all about how long people in traffic are delayed. And then we can look at the different values spent in here. So here are the variables: total delays per person, hours spent delayed in traffic, average arterial road speed, the average highway speed, and then the size of the city: small, medium, large, and then very large. And that gives us the following regression model. So I'm hoping you notice that there is one less variable present than what you might expect. Why is there no coefficient for medium? Yay! And then what does small mean? Okay, so I'm hoping you look down here and you notice that, oh my gosh, I have all the city sizes here present except for medium. That's a good indication that you've got an indicator showing up for city size. And it's going through all the possible values at city except for medium. Why isn't medium there? Well, that's because medium's the baseline, so it doesn't get an indicator. So basically, if we're dealing with a medium city, small, large, and very large will be turned off. These will all be producing zeros and not doing anything. And so it doesn't need an indicator variable. Then we want to ask ourselves, well, what does small mean? So we're looking at this coefficient right here, the one going with small. So it says that if traffic delays for a small city are about 3.6 hours per person per year, larger than in medium cities. So that's kind of interesting. But I think that kind of makes sense because small cities don't usually have as much well, not traffic pattern controls like lights and other things like that that are effective. They're more likely to have stop signs, which are, not as efficient when traffic gets heavy. Alrighty. So here's an example for you, taking some data from BurgerKing.com. Well, I think it was their website I got it from. Anyway, whatever. This is the second type of variable we're going to look at to make our linear regression models a little bit more effective, and these are what are called interaction terms. So I'm hoping you look at the meat-based versus non-meat-based dishes, and you notice, oh, well, their intercepts are pretty similar. That's not what I'm looking to change, but their slopes are different. So how do I fix slope? Well, you create a new variable that does some weird things, and they're called interaction terms. Interaction terms. Ooh, I said that badly. I'm sorry. So what we're going to do is we're going to first create an indicator. So it's going to be meat. If meat is present in the dish, then it flashes on as a 1. If meat is not present, then it's a 0. Woohoo! So this indicator is then used to make the interactor. So the interactor we have is carbs times meat. So carbs is what we're going to be using to do our normal, just linear regression slope variable. And then meat is either flashing on and off in this interaction term between carbs and meat. So what's going to happen is when meat is present, this will be a 1, and this interaction term will flash on. And when meat is not present, it'll be a 0, and then it does nothing. So let's look at what that does. So here is the output for creating this particular setup we've got. So notice we've got carbs present, we've got meat, and then we got carbs times meat. That right there is our interactor. Woohoo! And the one right above it, meat, is just the indicator, and we always include the indicator even with the interactor, even if it turns out that it doesn't do anything. So notice this is insignificant, so we probably shouldn't be including that indicator, which we'll probably remove it and then update things later. But for now, we're focusing on the fact of, oh, well, what does this really do, this interaction term that we've added? Yeah. So let's see. So here's what I want you to keep in mind. So if there is no meat, meat is 0. And so they have a 0 in the interaction term right there. So this does nothing. So we add 0. Just kidding. We get the following value. Ta-da! That's what our calories prediction equation will look like when that happens. Now, if meat is present, then look what we've got. We've got a 1 here and a 1 showing up here. So we've got a number times carbs. Notice that's the same as what we have over here. We have a like variable, so we can combine them. And then additionally, we have a constant with no variable, a constant with no variable. Since these are like, we can combine them. So the red part combines to make the following values below. And then the blue part combines to make these two times carbs. You're factoring out carbs, essentially. And you get the following. So what's happening is by including this interaction, it increases your slope, and including the indicator, as we've seen before, changes your intercept. Now, your intercept didn't change by that much, so that's probably why we're not including, or why the indicator that affects the intercept showed up as not significant. But the carbs value, oh my gosh, that's a huge change in carbohydrates. So we've seen a huge change in slope here. The slope increases quite a bit by, you know, over double. So I would say that's why that one's probably significant and the other is not. So this sort of follows what your instincts might be when it comes to doing regression with these terms. And this is more complicated than just doing simple linear regression for each of the groups. So one of the things to keep in mind when you're looking at this, you know, with the Burger King data, it makes sense. Why does the meat group have more carbs than the non-meat group? Well, because usually the meat dishes have a bun, which indicate that you would have a lot more carbohydrates in those than not. Next, we want to look at evaluating the model and whether or not it did a good job. So one of the more unusual things about multiple linear regression versus single or simple linear regression, you can just look at residuals and decide whether or not something is unusual and use it to judge whether or not we have an outlier. But with multiple linear regression, there are lots of ways you can be extraordinary. You might have an unusual y value, you might have an unusual x value, or you might have a combination of x values that make you be unusual. So remember when I say x values, there's more than one predictor present. So it could be that one of any of your predictors is the weird one, or it could be that all of them combine to make a weird one. So things to look out for. There's more, like always. Okay, so the first one we're going to look at is what's called a leveraging value. So a leveraging value is basically a outlier on steroids. Okay, so leveraging values tend to have unusual values in multiple different places. So their different combinations of predictors seem to create an unusual situation instead of just a single value. So they might not be necessarily far away from the mean for any particular single x, but together those combinations create something unusually large. So the easiest way to detect a leveraging value is to, actually look at what's called leverage. So leverages can be calculated by looking at the distribution of leverages, and these are usually called HIs. We're going to use technology to do this because they are in general difficult to calculate on their own. And the idea is that by looking at everything else being the same, we can detect leverage values by trying to keep everything around the mean and then looking at, is their combined distance they are away different? So it's a little bit like a z-score also, if you want to think about it that way, but it's a bunch of z-scores together. Okay, so back to the multiple regression diagnostic for the roller coasters. So speed, height, and drop. So what we want to do is we want to predict the speed of the roller coaster based on the height of the coaster and how far there is of drop in it. So I'm hoping you've been on a roller coaster before that has this big old hill in the beginning, and then you reach the top of the hill, and then you drop and create speed, basically. And I'm hoping that you look at these residuals and notice, well, there's nothing unusual going on here. I see nothing weird. So clearly the residual is not enough for you to be able to tell what's going on here because there are some unusual values present. Okay, so here is the distribution of the leverages. So I'm hoping you notice that there's this one just chilling out by himself. Oh, hey, back in stat 1, you would have called that an outlier because it is so far from the pattern of the rest of the data that there is no way that it should be included, or that it couldn't be an outlier. So what's unusual about this is the roller coaster in England called the Oblivion, and the Oblivion is unusual because it has a hole in it where it drops underground. And because of that, the drop of it is so much larger than the height, it makes no sense. In most of these, the drop isn't as tall as the height. So this is one coaster that looks different than everybody else. So of course its leverage value, when you combine looking at those two variables, is very high. So, when we're looking at regression analysis for this particular coaster, especially one involving height as a predictor, the Oblivion might be one you want to consider removing from your data just because it creates such a difficulty, and it actually improves your ability to predict a coaster's behavior in this case. The next diagnostic value we're going to look at is what's called the residuals and or the standardized residuals, or also the studentized residuals. These are all just fancy, well, I shouldn't say fancy, these are all just like misnomers, or what's the word I'm looking for? Nom de plumes for residuals and standardization. So standardized is just taking residuals and turning them essentially into a z-score of residuals, so it's easier to tell who's unusual and who's not. Remember that when we're looking at residuals, you might look at them and think, oh, well, that one's really big. Well, big is relative, and that's one of the problems that's difficult about looking at residuals. I've said this before, but if you're dealing with millions of dollars and you end up with a residual of $1,000, that's not very large, but you might look at it and think, oh, 1,000? That's a big number. Oh no. So you have to be careful when looking at these that you're aware of the size of your data. And if you're not, or if it's a data piece you're unfamiliar with, it's not a terrible idea to standardize these or studentize them so that they're easier to tell, or it's easier to tell if the value itself is unusual. If a data value has the rather unusual characteristic of having both of the values we just talked about being large, so high leverage, high studentized, or standardized residual, then we call it influential, which means that it's got to be influencing how your model is formed. It either is going to be unusual just because it happens to be an unusual piece of data that should be there, or because it's such an outlier that it really should be removed from the regression model. So when we get into doing my stat lab portion of this this week, you're going to be looking at two values that help you decide whether or not something is influential in measurement. The first one being Cook's D, or Cook's distance, and the other one being DD fits, or D fits. So just be aware that sometimes these have some different names, but I usually call it CooksD, and DD fits is the name that most stat programs use for DF fits. And we'll get into that in a little bit. So if either of these is extremely large, aka when compared to the histogram of other distances, then those cases should be checked out to see if they're influential or they just happen to be a value that's unusual and should be in your data. So we're checking to see, is it an error or is it just that this value happens to be a little unusual? Okay, so here are some Cook's distances from the speed example of coasters. And I'm hoping that as you look at this, you're like, well, I've got 4 of them up here that are unusually large compared to everybody else. So in particular, the accelerator and the volcano blaster, which I've never heard of either of those, which is kind of fun, are very large. And the Oblivion and Hypersonic are both up here too, which we've already talked about. The Oblivion in England, it's unusual for a couple different reasons. So you might want to look at this and be like, oh, well, these 4 appear to be different from everybody else. Is there a reason beyond the data that could be causing this? And it turns out that Oblivion, yeah, it's strange because of its huge drop that we saw investigated earlier. The other thing is that the rest of these on this list have what we called mechanically accelerated, not simply gravity driven. So if you look at the characteristics of these, oh, that might be the reason why they end up looking so different than everybody else. So when I say mechanically accelerated, I mean it's not accelerated by gravity. So earlier we talked about how as you go up to the top of the coaster and then you start to fall, that fall uses gravity to accelerate the coaster so that it finishes going through the ride. These are accelerated by some other means, and in some cases they are accelerated by even rocket engines. If you've ever been to Cedar Point in Michigan, or is it in Ohio? It's in Ohio, in the USA. They have one coaster there called, I think it's called a Top Thrill Dragster, that's accelerated by a jet engine, because that sounds safe. And it would probably also, like these, be considered unusual as far as influence measure goes. So if you reanalyze without the 3 accelerated coasters, you'll notice a striking effect that happens. And if you're having a hard time picturing this, you can compare it to the previous slides where we had this. But the biggest thing is, oh, well, then height no longer matters. Which kind of makes sense because of gravity drive compared to drop. They seem like they should be related if you're gravity driven. Anyway, so if we realize again with a simple linear regression, speed versus drop, the 3 accelerated coasters excluded, we see that not only does our model get better at analyzing, but it now seems to be doing the job pretty effectively. Woohoo! So one of the strategies you can use if you're not sure whether or not you should remove a piece of data, and I like this strategy quite a bit, is you can give them their own indicator, and that'll tell you whether or not those cases are significantly affecting what's going on. So what's going to happen is you can essentially do a test to see, is this data going to have a huge effect if I remove it? And you can look at the test statistic and the p-value to decide, oh, is this influential or not? Should it be removed or not? So if you do that and you give the accelerator, the hypersonic, and the volcano their own indicators, so they hop on and hop off, they'll tell you whether or not they are significant. So these blast coasters, hey, they don't fit with the model because look how tiny their p-values are. Clearly I should not be here. Yay! So anyway, and the other thing to notice is that if you look at the coefficient for blast, for the blast coasters for drop, this coefficient hasn't changed from the previous model by throwing in these indicators. So there you go. Okay, a little bit of wrap up. So look out for high leverage, look out for high studentized residuals. If you're not sure if you should remove them or not because they're extraordinary, you know, do the indicator test. That's the one that I tend to use the most when it comes to looking at this. And the big thing with these is that when you're looking at the extraordinary cases, it's a good idea to talk to somebody who's more familiar with the data. So if you're just somebody who's like showing up and just playing with this stuff versus somebody who's been working with it for their entire career, they're going to know more about those unusual cases than you are. Ask them, hey, is there something different about this group of people or individuals or data that could be causing this change, could be causing this difference that we're seeing? Okay, so here's an example again. Here's the traffic delays. So here's the scatter plot of highway MPG versus the residuals. The point plotted with an X is Los Angeles. In case you're having a hard time seeing that, that's right there. I'm highlighting it right now. Is Los Angeles likely to be an influential point on the regression? What do you think? Its residual is pretty high, but there are other values in here with that residual and even higher. But it's also got a highway mile per gallon that's much lower than everyone else's. Well, although LA has the lowest average highway speed of all cities in this study, the positive residual says the drivers lose about 7.5 hours per year more than the drivers in the model. And it may have an elevated leverage, but the residual isn't particularly large, again, because I've got other values that are at that value, at that residual or larger. So it's probably not influential, but, you know, it'd probably be a good idea to, sorry, you know, check not just the residual, but some other values for it to see. Alrighty, so be careful. How do we build a good best regression model? Well, we want to have few predictors, and we talked a little bit about this in 17. Fewer predictors means that you don't have an overinflated R squared. We want to have a relatively high R squared, but in general, when you're doing this, when you're evaluating your R squared, evaluate R squared adjusted over R squared to decide whether or not you are doing a good job, and then use R squared as an interpreter, in my opinion. Okay, relatively small value of S. We want to have all of our P's be significant and our F value be significant, aka our entire model be significant. We don't want to have any high leverages, high residuals, or high studentized values, and everything needs to look nearly normal. There's a lot of requirements, I'm hoping you notice that. And we want to make sure that our predictors are doing a good job. So this last bit about it being reliably measured, that means that you know your data is from a good source and relatively unrelated, aka you know independent. Okay, so how do you build a regression model the easy way? We can use what's called best subsetting and stepwise regression. These are automatic ways that you can automate this process. In the video attached to the case study, I will go through some very large wine data where I do not use either of these methods, and it takes forever to decide how to get this down to something that's good and significant. However, you can automate this process using best subsets and or stepwise. And one of these I do like much more than the other, just because I feel like it's a safer way to do this because it considers all the possibilities, but at the same time, it definitely takes longer to do. So it's one of those, you know, catch-22s. Do I want to spend more time on this or not? So let me describe these for you. Okay, so best subsets is my favorite. Sorry, it just is. Basically, it takes all of your possible combinations of variables. So if you've got 3 variables, there's only 6 combinations of looking at all 3 of them in different groupings, and it lists out for you all of what you can find for all these models. Like there are squared, there S, something called the Mallow CP, which I accidentally call the Mallow's Cup because that's the name of a candy all the time. And what we look for is which one of these is the best. So it lists you all the possible models. So in here I kind of describe it as, you know, if you have 4 variables, it'll give you all the 2 variables, all the best 3 variables, the best 2 variables, and the best 4 variables, on and on and on and so forth. So it gives you the best combinations of these that you can find, and then it's up to you to decide which one you should be using. The downside to this is clearly if you have a computer doing this, it can take a super long time if you have a lot of data and a lot of variables. So if it's a large data set, this can take forever. So I think it's best to use this if you can eliminate some variables first, by looking at are they linear, are they appropriate, that kind of stuff, and then use this. Okay, stepwise is a little bit easier. There's actually 2 forms of stepwise. It either builds the regression by taking some initial model and then adding variables in, adding predictors in to see if they improve the model until it hits a certain amount of good predictors, and this is difficult. The other one is the stepwise backwards, which takes all the predictor variables and then removes them until it gets down to something that's significant. So it removes them one by one until it gets down, which is usually the method most people do if they do this by hand. Let's just include all of them and then eliminate whoever is insignificant to get down to the best model. Okay, so what are the challenges behind this? For large data sets, being able to check accuracy, missing values, consistency, and reasonableness is a huge effort. As you go through this, there's lots of ways you could end up making errors. In particular, as you have more and more variables present in your model, the more likely it is that you have a type 1 error occurring. And best subsets and stepwise really don't check assumptions and conditions. I don't know why I can't say that today. So the part earlier where I was saying, hey, check to see if they have linearity first. That's a human check. You can check that first to decide if it should be used in your stepwise or in your best subsets. And you still have to check all these conditions even after it produces a model for you. You should be checking your residuals. Are they nearly normal? You need to go through all the steps we discussed in 17, even if Minitab or other software produces the equation for you. Okay, so one of the biggest concerns that you can have when creating your model is that you might see some variables that exhibit what's called collinearity. Collinearity is when your predictors actually can be predicted well from other things. So they have some relationship overlying with other predictors you have present, and because of that, they sort of overinflate everything. So the problem with this is if you have indicators of collinearity, this means that you actually have variables that are predicting with each other what already each other did. So it's a little bit like a lurking variable that we talked about previously. There's some other relationship that's causing this to be inflated. So if you have two variables that aren't just correlated with the response variable, but are correlated highly with each other, the more likely it is that it inflates your model. And we call this variation of inflation factor. So this is usually called, instead of just VI, it's called VIF. Woohoo! Variation of inflation factor. So it leads to having a smaller test statistic and a correspondingly large p-value for what's going on because it looks like something's more insignificant than it actually is. So recall our housing prices example when we look at living area versus bedrooms independently. So up above this first example here, oh gosh, that looks kind of terrible, sorry. This first one is looking at just living area to predict your value, and the second one is bedrooms. So as you look at this should look a little familiar since we did this example previously, and I'm hoping that you notice that their slopes are very different. So as you increase living area, it costs about $113 more. As you increase number of bedrooms, you get about $48,000 more for that house. So it seems like these two are related and for a very good reason. Because if you have more bedrooms, you probably have more living area. Or if you have more living area, you probably have more bedrooms. These seems like they should be related, not just to price. And if you include all of them, hey, they all look significant. What? And in particular, the multiple regression model, including housing price along with living area and bedrooms, the coefficients seem counterintuitive, and we saw this before. Hey, number of bedrooms is negative now for its coefficient. That shouldn't happen. But we talked about how if you increase the number of bedrooms and you don't change living area, you end up with tiny bedrooms, then nobody wants to buy your house. This does reduce the value of your home. And what if instead we looked at number of rooms instead of just bedrooms? So this is a little bit of a different scenario. If I look at number of rooms, the value is a little bit different. So number of rooms would be including not just bedrooms, but bathrooms, living rooms. Yes, you can have multiple living rooms. My house has two. It's weird. We call the other one the sunroom. And just, number of rooms in general. Clearly, if you have more rooms, you probably have more living space, and aka more living area. These seem like they're related as well. Let's see what happens when we include both of those. Ta-da! Hey, suddenly rooms is hugely insignificant. I wonder what happened. And in particular, look at what happens with the standard errors. So if you want to flip back to the other slide, hey, these have changed hugely compared to the previous model. And I also usually look at p-value. Something appears to have happened when I combine these. So what we want to look at is what's called variation of inflation factor. I've mentioned him before. He's very important when it comes to deciding collinearity. So I'm going to warn you right now, this is a little bit of a judgment call on your part. So if you look at two variables and their variation of inflation factor and it's something small, aka like close to 1, then they're not correlated. If it's between 1 and 5, then they're moderately correlated. If it's above 5, then they're incredibly highly correlated. One of them needs to be removed. So I've seen ones above 10 before, so don't let that 10 in there fool you. It used to be in the olden days, it only went up to 10, so whatever. You can get ones above 10. In fact, I'm going to do one above 10 in in your your case study. Anyway, so things to watch out for. Just look at variation inflation factor. It'll indicate high collinearity between your variables. That should point you towards, oh my gosh, one of these is definitely not going to be included. And then I generally just use who's insignificant to remove them. So be careful. This first sentence here is the easiest way to detect collinearity or suspect it. So if you look at a regression model and you're like, wow, it looks really good, but none of my t's are significant, that means you definitely have collinearity. You should definitely adjust and try removing some of your variables from the model to see what happens. Or just check the correlation between your predictors to see if you can pick out who's going to be highly correlated with who and who should be removed for that reason. Okay, so I've already stated removing. Here's how you should decide how to remove. The variables that are most reliable and measure should be the ones that are kept. What do I mean by that? The ones you know for sure are good data you should keep. The ones that are least expensive to find, remember we are business people, stuff that is inexpensive to acquire is going to be the stuff you want to keep. Variables that are inherently important to the problem. This one's a little bit harder to judge. So for instance, in the roller coaster example, I know that many of mine are gravity driven, and therefore I definitely should keep either height or drop, because there must be something in the way that the coaster begins its travel to indicate how it's going to behave. And I think that that is incredibly important, and that's a judgment call. And the last thing you should do is anything you made that was new. So if you made a new variable using either indicators or dummy variables, or, well, any variable that you created, if you coded data to create a variable, that's the ones you should look at removing first, because they're less pure than stuff that came from the raw data. Okay, so, hey, here's a fun fact. Did you know that in Olympic skiing, the start order actually has a huge influence on the time it takes you to complete the course? Hey, fun facts. In downhill skiing, the runs actually get slower as the day wears on because the snow becomes more packed, which is kind of interesting. Powder is actually easier to slide through in case you've never been skiing. So we want to see, does start order have a big effect on time? And it looks like it does. But there are some problems with this regression. Oh no! Residuals! Those look scary! And if you would have bothered to check the scatter plot of the data before you began, you'd notice, this appears to have a lovely cup to it too. This doesn't look linear. You know how I keep saying you need to check scatter plots for linearity? You should totally do that before you begin anything else. And here's why. Because sometimes then you make a model and it's crap, like the residual's bad. Looking up here, I'm hoping you notice, oh my gosh, this seems to have a cup shape to it too. Darn. This is going to fail linearity in two ways. It doesn't have linear residuals, and it doesn't have linear shape in its original scatter plot. What do you do when this happens? It's not panic, and it's not give up. Never give up, never surrender. Instead, you got to figure out a way to make this quadratic. And the answer is, well, I'll just take my data and square it and add it to the model. That's it. This is how you can fix the problem of I have a piece of data that's nonlinear. But that might be not the only thing you need to do. Uh-oh. So you look at this and you're like, hey, it looks pretty good. There's start order, the original variable, and then start order squared. So you have to create this yourself. You can see that I have a typo in this because when I was writing the word start order to make this square fit, I had to call it start order, which is funny. Hey, and they're both significant. Yay! And my F ratios is large, so it's probably significant. And look, my R squared adjusted is good. It's in the better than meh range for sure. This is looking very promising. And then you look at the residual and it looks pretty unstructured, but at the same time you're a little unhappy with it because it looks very tight over here and then wider and more widespread in the rest of the data. But that might just be because more of your values are in the predicted range appear in this range of values. Okay, is there anything wrong with this? Well, the unfortunate news is, well, yes. If you look at the coefficient for start order from the original, I'm looking at this value right here, and then compare it to the coefficient for start order down below when you included the quadratic term, it changed sign. That's a good sign that you have collinearity. So how do I fix collinearity? With quadratics, it's actually really easy. You include a term that will not be correlated to the original. So I'm hoping you recognize that right here I'm using the mean of start order. This is going to remove the relationship start order squared has with start order. So I'm subtracting start order from the mean and then squaring it. So I'm going to be using the calc menu to do this when you watch me do it with the videos. And if you do that and then redo your model using this new start order minus the mean squared, you notice that, hey, my coefficient for start order is back to being something positive. I appeared to have fixed this problem. Also, if you look at the VIF values for start order versus start order minus mean squared, it comes out as, oh, these don't appear to be correlated, which is a good thing. Cool. So why bother with quadratics? Well, to be able to predict. Usually whatever variable we have for response is something we're interested in studying and we want to know more about. Maybe it's our adjusted gross income or the profit we predict that our company will have or something useful that we want to know. So we want to understand relationships or we want to have good predictions. That's why we might want to bother with quadratics and or just regression in general. Let's look at an example using lobster data. So this is lobster, well, look, water temperature off the coast of Maine, which has a seasonal effect for the lobster fishermen because temperature has a big impact on when the lobsters start to, I think it's when they start to move. Anyway, I don't know enough about lobsters to be able to tell you what's going on here. I should use a lobster expert next year. So here you go. That doesn't look straight. Oh no, what do we do? Oh crap, we're still in the quadratic one, aren't we? Hey, I bet you can guess. So the first thing you notice is, hey, super not linear, so we should probably include a quadratic term to see if that will better produce a model that can predict water temperature. Woohoo! So you add in year squared. There she is. And if you look at it, it's super tiny, which is kind of scary. Oh no. And then it's significant. Everybody's significant. P-value. Oh, I didn't include F on this, but I did include my S value. Where did my R squared adjusted go? I meant to put it right there. Oh, I'm a terrible person. Okay, anyway, here's what's important. Hey, year's negative. Does that make sense? This tells us that, you know, the temperature is dropping every year by 19 degrees. Huh. Strongly negative. I wonder if that's correct. Well, since clearly when you looked at the graph, it's not always negative, it's not always dropping in temperature. So that is a good indicator that when comparing year and year squared, these two are likely highly correlated. What you should do next is, instead of using year squared, use year minus the mean of year squared and see if that fixes your collinearity problem. Additionally, if you're ever questioning collinearity, you can make Minitab do VIF, which will tell you definitely if you've got some collinearity happening. So what can go wrong? Oh my gosh, collinearity, right? And influential measures. Look out for missing data. If you have something missing, that's not very helpful. Don't forget to check the linearity assumption. I said this a couple times, but you should always be doing scatter plots first, working on regression later. And then look out for parallel regression lines. That's a good indicator that you need an indicator. So, what have we learned? We learned about indicator variables. Here are their details. We learned about how to diagnose whether or not something was influential based on individual cases and looking at leveraging values and studentized residuals to decide that. Additionally, we talked about two measurements that I'm going to calculate for you using Minitab called Cook's D and DVD fits. And these are great for deciding whether or not something is a measure of influence. Be aware that when you're producing a multiple regression model, there are many predictors available. We want to have a balance between few predictors a relatively high R squared, a relatively small s, aka residual standard deviation, and we want to have small p-values for our coefficients. Yay! And so we talked about one of the ways you can automate this is using best subsets and or stepwise regression. We will see both those when we do our mini tabs. Mini tab is not plural. I don't know why I just did that. Okay, so when it comes to recognizing collinearity, watch out for variation of inflation factor. Minitab automatically produces this for you in multiple linear regression, so that's good. And then look out for everything looking fine and significant, but yet coefficients changing. That's a good sign that you've got some collinearity happening. And then the other thing is you should remove predictor models, not just based on who's insignificant, but based on who seems to fit what you need to do best and or cost. Lastly, we talked about how to fit quadratic terms into our regression model. Be careful. It's very easy to end up with something collinear when you add a square. And we talked about how to fix that. It's actually pretty easy. We just end up using, instead of the variable squared, we just take that variable. Why is this yellow? I meant to do that in black. Woohoo! Take that variable, subtract its mean, and then square it instead as our new variable. So just be aware of those two fixes. That's all I've got for you. Welcome to the end of linear regression. Hope you enjoyed it.